A rotating machine rarely fails without warning. It speaks first. It vibrates, it shifts, it heats, it drifts, it produces noise, movement, instability, axial displacement, abnormal casing response, bearing temperature rise, speed excursions, and sometimes the most dangerous signal of all, overspeed. But here's the real question I want you to sit with. When that machine speaks, does your protection system truly understand what it is saying? Because in real plant engineering, a machinery protection system is not just a vibration rack. It is not just a set of probes, cables, relays, monitors, and display screens. It is the engineered line between early warning and catastrophic failure. And if you are a design engineer, trainee instrumentation engineer, rotating equipment engineer, reliability engineer, or process control professional, you need to understand this deeply. A machinery protection system is not decoration. It is not a dashboard. It is not only a vendor package. It is a protection chain, sensor, cable, shielding, grounding, signal conditioning, monitor logic, alarm set point, shutdown set point, voting logic, relay output, trip interface, field calibration, proof testing, documentation, maintenance discipline. One weak link in that chain can defeat the whole system. And this is where many engineers make their first serious mistake. They think the job is to select instruments. But machinery protection is not instrument selection alone. It is failure mode thinking converted into hardware. You are not just asking, what sensor should I install? You are asking, what machine failure am I trying to detect? How quickly can it develop? What signal proves it is happening? What signal could mislead me? And what should the system do when that signal crosses the danger boundary? That is the mindset. That is the difference between monitoring and protection. Monitoring tells you something is happening. Protection decides when continued operation is no longer acceptable, and that decision must be reliable. Let's break this down in a practical way. When you specify radial shaft vibration, you are trying to understand rotor movement relative to the bearing system. This is critical for machines with fluid film bearings, turbines, compressors, large pumps, and similar rotating equipment. The rotor may show imbalance, misalignment effects, oil whirl, oil whip, rubs, looseness, instability, or abnormal dynamic behavior. But two things must be true. First, the probes must be located where the movement matters. Second, the shaft target surface must be suitable for measurement. A proximity probe does not magically know the difference between true vibration and bad target condition. If the shaft surface has mechanical runout, electrical runout, marks, discontinuities, plating issues, magnetic variation, or poor finish, the probe can produce a signal that looks like vibration but is not true vibration. And if you simply accept that reading without questioning the measurement chain, you may alarm unnecessarily, trip unnecessarily, or worse, miss the real problem because you have lost confidence in the system. That is why a good engineer does not only ask, what is the vibration value? A good engineer asks, can I trust this vibration value? Probe orientation matters. Probe gap matters. Probe tip clearance matters. Distance from bearing matters. Cable length matters. Oscillator to modulator matching matters. Grounding matters. Runout matters. Field calibration matters. The display value is only the final number. The truth lives in the installation. Now think about axial position monitoring. This is not a casual measurement. Axial movement can quickly become thrust-bearing distress. When a rotor moves toward active or inactive thrust limits, the machine is telling you that thrust balance, load, internal condition, or bearing integrity may be at risk. If your axial probes are observing the wrong surface, you may not be measuring real shaft axial position. If the target is loose, non-integral, or mechanically questionable, the reading can become misleading. If the active thrust direction is misunderstood, the interpretation can be wrong. If the probe is not correctly zeroed during thrust float setup, the alarm and shutdown points may look correct on paper but behave incorrectly in service. This is why axial position protection is both mechanical and instrumentation engineering. You cannot design it from the instrument index alone. You must understand the thrust bearing, rotor float, active thrust direction, inactive thrust direction, target surface, probe mounting, adjustment access, and calibration method. A machine does not forgive shallow engineering. Now let's move to casing vibration. Casing vibration is useful, especially for pumps, motors, fans, gearboxes, and machines with rolling element bearings. But casing vibration is often misunderstood. Shaft vibration and casing vibration are not the same thing. A shaft probe tells you how the rotor moves relative to the bearing. A casing accelerometer tells you how the external structure responds. That response depends on bearing condition, machine stiffness, foundation, mounting, resonance, loading, and frequency content. So if you use casing vibration for protection, you must define what you are actually protecting against. Are you monitoring velocity over a practical frequency band? Are you using acceleration only for condition indication? Are you filtering out noise? Are you avoiding unfiltered overall vibration as a nuisance trip generator? Are you mounting the accelerometer on a proper machined surface? Is the mounting stiff enough? Is the cable protected? Is the accelerometer electrically isolated? Is the frequency range meaningful for the machine type? This is where measurement discipline matters. A poor casing vibration installation can make a healthy machine look bad. A poor filter selection can make noise look like danger. A weak mounting point can turn structural resonance into false alarm. So again, the question is not only what does the vibration value show? The question is, does this value represent the failure mode I care about? Now, bearing temperature. Bearing temperature looks simple until you ask one serious question. Where is the sensor located? A temperature sensor does not measure the whole bearing. It measures the temperature where it is installed. If it is not near the load zone, if it is not properly embedded, if it does not have positive thermal contact, if it is placed away from the critical oil film region, then you may get a clean, stable, precise reading that tells you very little about actual bearing distress. That is a dangerous kind of precision. A wrong temperature measurement can look professional, it can trend beautifully, it can sit calmly on the screen, but if it does not represent the thermal risk zone, it is not protection quality information. For sleeve bearings, tilting pad bearings, and thrust bearings, location matters. Direction of rotation matters. Load on pad or load between pad design matters. Length to diameter ratio matters. Active and inactive thrust bearing arrangement matters. And for motors and generators with insulated bearings, sensor installation must not compromise insulation integrity. This is why you need coordination between machinery vendor, bearing design, instrumentation design, and maintenance access. A sensor is only as useful as its location. Now let's talk about piston rod drop in reciprocating compressors. This is one of those measurements that looks simple but demands careful interpretation. Piston rod drop is used to infer rider band wear and protect against piston to cylinder contact. But the probe is not directly measuring rider band wear. It is measuring piston rod position relative to the probe. That rod position can be affected by rider band wear, yes, but also by rod runout, crosshead alignment, rod deflection, process load, thermal growth, and crank angle. So if you treat rod drop as a simple number, you can misread the machine. A good rod drop system must consider top or bottom probe mounting, probe gap strategy, rod coating, scale factor, thermal growth reset, triggered mode, average mode, and trending. Triggered mode is especially powerful because it allows you to measure rod position at a consistent crank angle, ideally where non-wear effects are minimized. But that trigger point must be established carefully during commissioning. One isolated rod drop value can mislead you. A well-commissioned trend can protect you. That is the difference. Now, overspeed. Overspeed is the fastest and most unforgiving protection problem in rotating machinery. When overspeed happens, you do not have the luxury of long interpretation. The system must detect, decide, and actuate quickly, and overspeed protection must be independent, not shared, not casually integrated, not dependent on a process controller, not dependent on another system's sensor, not routed through unnecessary logic that can delay action. An overspeed detection system must be dedicated to the overspeed function. It must use independent speed sensing channels. It must apply proper voting. It must have reliable power. It must support testing. It must capture peak speed. It must interface correctly with the shutdown chain. But here's the part many engineers miss. Electronic response time is not the whole overspeed response time. The total system includes sensor pulse generation, speed sensing surface geometry, signal processing, logic response, relay actuation, solenoid response, trip valve response, stored energy in the machine and process, and rotor acceleration rate. A fast electronic module cannot compensate for a slow final trip path. A good overspeed design asks, how fast can the rotor accelerate? How many pulses per revolution are available? Can the sensor detect low speeds? Can passive magnetic sensors generate enough signal? Should active magnetic sensors or proximity probes be used instead? Will sensor gaps survive abnormal vibration? Could intrinsic safety barriers add delay? Are speed sensors shared with any other system? Are the power supplies redundant? Can each channel be tested? Does 2 out of 3 voting work as expected? Will a single failure alarm but not trip? Will 2 failures trip where required? Have relays and final elements been tested? Overspeed protection is not a place for assumptions. Now let's talk about wiring, shielding, and grounding, because this is where good design often gets damaged in the field. A machinery protection signal is often small, sensitive, and exposed to a hostile environment. Heat, moisture, vibration, electromagnetic interference, radio frequency interference, ground loops, power cable coupling, poor shield termination, wrong conduit routing, water accumulation, bad junction boxes, loose connectors, cable damage. All of these can corrupt the signal, and when the signal is corrupted, your system may become noisy, unreliable, or ignored. That is one of the biggest dangers. Once operators lose confidence in alarms, protection culture starts to weaken. Signal wiring must be segregated from power wiring. Shielding must be terminated correctly. Cable runs must respect limits. Field junctions must preserve shield continuity. The shield must not become the common return. Instrument common must remain isolated from ground except at the intended point. Conduit must have drains. Underground conduit must be treated as a moisture risk. Connectors must be protected. Instruments must remain accessible, and protection system components must not be hidden behind insulation, piping, covers, or poor layout. A system that cannot be accessed will eventually be bypassed. A system that is frequently noisy will eventually be distrusted. A system that is not documented will eventually be mismaintained. Now let's discuss alarm and shutdown philosophy. Alarm and shutdown are not the same. An alarm is a warning. It exists to trigger corrective action. A shutdown is a protective decision. It exists to stop operation before damage becomes unacceptable. You should not set alarm and shutdown values casually. You must understand machine behavior, transient conditions, failure mode speed, operating envelope, false trip consequence, and failure to trip consequence. Voting logic matters. For radial, vibration, and axial position, dual voting can reduce false trips caused by one bad channel, but it must be understood correctly. If one channel fails, the system may alarm on fault but not trip. That may be appropriate, but operations must understand protection is degraded. For overspeed, 2 out of 3 voting gives both reliability and fault tolerance, but only when the 3 channels are truly independent. Time delay matters. Too short and you trip on spikes. Too long and you miss a fast developing event. Set point multipliers matter. They can be useful during startup in specific cases, but they are dangerous if used casually. If you multiply set points simply to avoid nuisance trips, you may be weakening protection when the machine is vulnerable. A set point multiplier must be justified, controlled, indicated, logged, and reviewed. If it is active, operators must know it. If it is not needed, do not use it. Do not desensitize protection to hide poor design. Fix the design, fix the installation, fix the machine, fix the measurement. Now, circuit faults. A circuit fault is not just an instrumentation nuisance. In machinery protection, a circuit fault means part of the protection layer may be impaired. A failed probe, open circuit, short circuit, failed accelerometer, failed power supply, failed monitor channel, lost communication, or bad transducer can reduce your ability to protect the machine. So circuit faults must be visible, they must be enunciated, they must be acted upon. A healthy channel should be positively indicated. A faulted channel should not disappear into the background. Maintenance bypass should be controlled and visible. Disarmed shutdown status must be obvious. Never normalize protection impairment. Never let a bypass become permanent. Never treat a faulted protection channel as just an instrument issue without understanding the risk. Now, testing. This is the point where design becomes real. A machinery protection system is not proven because the rack powers up. It is not proven because the display shows values. It is not proven because the vendor submitted certificates. It is proven when the installed system is tested from input to output. For proximity probes, you need gap voltage checks and calibration curves. For temperature channels, you need simulation at multiple points. For accelerometers, you need shaker testing where applicable and full-scale electronic simulation. For tachometer and overspeed systems, you need speed simulation and trip verification. For relays, you need contact verification. For bypasses, you need indication verification. For communication, you need data verification. For shutdown, you need cause and effect proof. For integration with control systems, emergency shutdown systems, machinery diagnostics, and operator displays, you need functional confirmation. A correct screen does not prove a correct trip. A correct monitor value does not prove relay action. A correct relay action does not prove the final element responds. Testing must follow the complete chain, and documentation must capture the result. Because months later, when the machine alarms, trips, or behaves abnormally, the first question will be, what was the design intent? What were the set points? What was tested? What changed? And what proof do we have? Documentation is not paperwork. Documentation is protection memory. It preserves the engineering logic after the project team has moved on. Now let me make this highly practical for you. When you review a machinery protection package, do not only check tag numbers, check the failure mode. Why is this channel required? What does it protect? Where is the sensor located? What surface is it measuring? How is it mounted? What is the cable route? Where is the shield grounded? What is the monitor range? What are alarm and shutdown set points? Is voting logic defined? Is time delay defined? Are bypasses controlled? Are relays normally energized or de-energized as intended? Is overspeed segregated? Are speed sensors independent? Are power supplies redundant where required? Are hazardous area requirements addressed? Can the system be maintained safely? Are spares defined? Are calibration records available? Are field test records available? Are as-built drawings complete? If you cannot answer these questions, the system is not fully engineered. It may be purchased, it may be installed, it may even be running, but it is not yet fully defensible. And that is the standard I want you to hold as an engineer, not does it work today, but will it protect correctly when the machine moves toward failure? Because rotating equipment failures are expensive. They damage bearings, rotors, seals, couplings, gear teeth, impellers, blades, casings, foundations, production schedules, and sometimes people. Machinery protection is not about fear. It is about disciplined confidence. When designed well, it gives operations trust. It gives maintenance direction. It gives reliability teams evidence. It gives design engineers accountability. It gives the machine a voice that can be heard before damage becomes irreversible. So here's the final takeaway. A great machinery protection system is not the one with the most channels. It is the one where every channel has a purpose. Every sensor has a valid location. Every signal has integrity. Every alarm has meaning. Every shutdown has justification. Every bypass has control. Every relay has been tested. And every document supports lifecycle maintenance. If you are a trainee engineer, learn this early. Instrumentation is not just measurement. It is judgment converted into hardware. If you are a design engineer, remember this. Your drawings, specifications, and data sheets are not administrative deliverables. They become field reality. They decide whether a plant runs safely, whether a machine trips correctly, and whether a failure is prevented or merely recorded. A rotating machine will always tell you something before it fails. Your job is to design the system that listens correctly. And when listening is no longer enough, your system must act. If this gave you a sharper way to think about machinery protection systems, like this video, share it with a young engineer, and subscribe to the channel for more instrumentation, process control, automation, and engineering design tutorials. You can also follow my LinkedIn newsletter where I break down practical engineering topics into white paper level insights for design engineers, trainee engineers, and working professionals who want to build real technical depth. And if you are working on process instrumentation, control systems, rotating equipment interfaces, protection philosophy, or engineering design reviews, get in touch. Because the difference between a system that merely monitors and a system that truly protects is not luck. It is engineering discipline.